All right, so 11 units down, 1 to go. Now, the burning question in your head, though, is like, wait, okay, so we've done 11 units already this year. It's been a long year. I'm really tired. But at this point, I'm pretty comfortable with this X and Y stuff. What if there's a third variable present? What does that do? Does it make things awkward? Is it even possible? What is Mr. Rumpf even talking about at this point? So that's what we're going to be looking at here with parametric equations. Before we get into that, though, we want to acknowledge this is our last unit. It's been a good ride. But I brought in a friend of mine. He wants to say a few words of wisdom. So I'm going to have my friend Sean, he's just going to say a few things real quick.
Just know you'll never be alone. I hope that you get everything you want and that you chose. I hope that it's the realest thing that you ever know.
All right, so that was my friend Sean. He just wanted to say a few inspirational words. Like I said, he heard about this class, thought it was kind of cool with these videos. But moving on, back to the parametric equations, because that's what we're talking about here. So we want to understand what is a parametric equation, how to graph them, how to convert from parametric to rectangular, and from rectangular to parametric. First, what are parametric equations? In order to understand that, we need to understand what is a parameter. So in the context of parametric equations, a parameter is a third variable, essentially. Parametric equations are sets of equations in terms of the parameter. A plane curve is the resulting path of a set of parametric equations. Basically, it's the graph. We just, in this case, are referring to it as a plane curve as well, but it's a graph. The orientation is the direction of the curve for increasing values of the parameter. So that's what's going to be new here in terms of what the graphs are going to look like, is we're actually going to see graphs that we've seen before, but now there's going to be intentional direction to the graph based on the parameter increasing. So let's look at what we mean by this. Okay, here is an example of some parametric equations. Here I have x equals t squared minus 2t and y equals t plus 1. T is the parameter. It does not appear in the graph of the curve. So we're going to graph this in a minute. Not yet, in a minute. But we want to understand we're not going to actually see t in the graph. We're going to see x and y values, and the direction to the curve is going to be based on t. So the question is, why? Why do we care, right? Well, we're going to hopefully discover that throughout this video. But we want to understand we're still just plotting x and y points, okay? So we're going to pick values of t. T is going to start somewhere. Usually it starts at 0, but it doesn't have to. It depends on what the context of t is. A lot of times t can be time, but it does not have to be time. It can be an angle. It could be just some other parameter. But essentially, you're going to have a specific value for x based on t and a specific value for y based on t. But what that's going to give you is an xy point. So we're still going to plot the point the same we would if we just had a rectangular equation, which we're going to look at how we convert from parametric to rectangular and vice versa. We can also kind of think of this like a vector, and actually in the next video you're going to see parametric equations as vectors. But what I mean by that is vectors have the I and the j component. Here we have the x and the y component. But we should be familiar with the x and y component. Emphasizing again, t is the parameter. It does not appear in the graph of the curve. The parameter usually is giving a direction to the curve. And again, it can represent time. It could be an angle. It could be something else. Okay, so now let's actually get to this example. So we want to sketch the curve represented by the parametric equations, x equals t squared minus 2t, and y equals t plus 1. So the question is, well, how do we do that? Good question. Well, we're going to make a table of values, just like when you first learned to graph rectangular equations. The only difference is now we're going to have t, x, and y. So we're going to pick values for t. So I'm just going to start at 0. So I'm going to say 0, 1, 2, 3, and let's do 4 for fun. So if I plug in 0 here, x gives 0. If I plug in 0 here, I get 1. If I plug in 1 here, I get negative 1. And if I plug in 1 here, I get 2. If I plug in 2 to the x equation, I get 0. And if I plug in 2 to the y equation, I get 3. If I plug in 3 to the x equation, I get 3. And if I plug in 3 to the y equation, I get 4. And let's do one more. So if I plug in 4 to the x equation, I get 8. And if I plug in 4 to the y equation, I get 5. So now if we want to graph this, we can plot points. So let's do negative 1 is the farthest left we went, and then 1, 2, 3, 4, 5, 6, 7, 8. And we're going up to 1, 2, 3, 4, 5. So let's plot some points. I know I have the point 0, 1, negative 1, 2, 0, 3, and then we go to 3, 4, and then 8, 5. So what does this curve look like then? So since we started with t equals 0, the curve looks like this, but what we want to understand is that there was direction to it. So the direction is based on t, or the parameter, increasing. That's the new thing with parametric equations. Okay, what does it mean to eliminate the parameter? Great question. Eliminate the parameter means convert to rectangular. So rectangular is what we're used to, just an equation in terms of x and y. How do we do this? Great question as well. We are going to solve one equation for the parameter and substitute. So if I look up here, it's very easy for me to say, okay, y minus 1 equals t. So I solved one of the equations for the parameter. So then for a rectangular equation, I could say x equals y minus 1 squared minus 2 times y minus 1. So that would be the rectangular form of this set of parametric equations. So our process is eliminate the parameter, and now I have a rectangular equation down here in terms of just x and y. Notice that it's not a function, but we also kind of knew that already because we saw our graph here. So again, just to emphasize the picture of the graph, as t increases from 0, notice that x first decreases, but then as we continue on, x increases. So the path here starts out going to the left, and then it goes to the right. And what we can see from our rectangular equation, well, this is just a quadratic in terms of y squared, but now we have this parameter, so it gives us direction and potentially more context to the problem. So I want you to try this one. I want you to sketch the curve represented by the parametric equations. I want you to indicate the direction of the curve, and then I also want you to eliminate the parameter, so rewrite it in terms of just x and y. Pause the video, unpause when you're ready to check. All right, so one thing hopefully you notice here is that because of our x equation, t has to be greater than or equal to 0, right? No matter what the context of t is, it cannot be less than 0, because then we're going to get imaginary values for x. So here we can see I eliminated the parameter. So I said t equals x squared, e has to be greater than or equal to 0, which means that x has to be greater than or equal to 0. so y equals 1 minus x squared. I could also eliminate the parameter by solving the y equation. So I could say t equals y minus 1, so x equals the square root of y minus 1. So notice that there's two different ways in which I can eliminate the parameter. If I graph this, I can see my points. Well, again, it's just a quadratic, but it's only half of a quadratic because of my restrictions on x. So notice that depending on how I eliminated the parameter, here I need to put that restriction on x because it carries through from the parametric equation with t. Here I don't need the restriction because it's built into this form of the of the rectangular equation. But again, back to the graph, so I plotted a few points, and I can see the direction as t increases. This is the direction that the graph is going to travel. I want you to try another one now. This one's going to be a little bit more difficult. So what is the parameter here? Well, first of all, we need to identify that. The parameter is theta. So I want you to eliminate the parameter, sketch the curve, and indicate the direction. So pause the video, unpause when you're ready to check. I will give you a hint. You might need to use some trig identities. Okay, so here you can see the table that I made, plotting some points. So I picked some values for theta that I knew would work out nicely, and found the corresponding values for x and y. And so this is what the graph looks like. This is where I started with theta equaling 0, and then notice the path that the graph is actually taking, and it just creates this loop. And this loop will actually just continue forever if I keep plotting points. Now, how do I actually eliminate the parameter here, though, and get this into a rectangular equation? Great question. You need to use some trig identities. So notice sine of 2 theta. Well, what's the double angle identity for sine? The double angle identity is 2 sine theta cosine theta. Or since there was already this 2 here, I can make this y equals 4 sine theta cosine theta. But cosine theta is x. So I have y equals 4 sine theta x. So y over 4x equals sine theta. Okay? Well, I still haven't eliminated the parameter yet, but I know from trig identities sine squared theta plus cosine squared theta equals 1. I know sine of theta is y over 4x, and I know cosine of theta is x. So boom, eliminated the parameter. So I have y over 4 quantity squared plus x squared equals 1. I can simplify this a little bit if I want. It's not terribly useful, but I got y squared equals 16x squared times the quantity 1 minus x squared. You could distribute this. There's no really proper way necessarily to write this. If you can solve for y, you want to try to, but either way, we know it's not a function. All right, last thing. Now, what if we have a rectangular equation and we want to write a set of parametric equations? Again, I'm actually going to have you try this on your own because it's kind of hopefully pretty straightforward. You have to be given some relationship between a parameter and one of the variables to start. So you're actually going to do, there's two different problems here. Part A, t equals x, and part B, t equals 2 minus x. So try to do part A and part B, write a set of parametric equations given the rectangular equation and given the relationship for part A and the parameter and the relationship for part B and the parameter. So pause the video, do that, unpause when you're ready to check. All right, so for part A, it is this straightforward. T equals x, therefore my parametric equations are x equals t and y equals 6t squared minus 5. For part B, still pretty straightforward. If t equals 2 minus x, then x equals 2 minus t, and I can plug that into my y equation, y equals 6 times the quantity 2 minus t squared minus 5. Multiply that out if I want. Again, it doesn't matter. Y equals 19 minus 24t plus 6t squared. Okay, so it's that straightforward when we are going from rectangular to parametric. You have to be given some information. But back to why do we care about parametric equations? Well, we use them to describe curves in the plane when one function won't do, and to describe paths where we want to have this other parameter. A lot of times, like I said, it's time, but it doesn't have to be. How do we do this? Plot points, eliminate the parameter. We can use a calculator by changing your mode. So there's many ways in which we can do this. Here's our conclusion. Converting from parametric to rectangular, solve for one equation, eliminate the parameter.